Hi, everyone. I thought I would do something a little bit different with relativity, and this is based on a little bit of feedback from the class as well as last year's class, and the realization that this is really weird stuff and it deserves a little bit of a deeper dive. And so, what I'm doing is looking at a couple of things in relativity with a little bit more emphasis, a little bit more detail. And I want to start with the twin paradox. Now, the twin paradox is one of the centerpieces of our attempts at understanding the weirdness that is relativity. And by the way, if you find this logically inconsistent with what you experience in everyday life, then yeah, we don't live at relativistic speeds. So a lot of this isn't going to seem to make sense because we can't perceive it. However, we do see these effects when we have high enough precision instrumentation, and many applications like GPS satellites require relativistic corrections. So these things are real and they're not illusions, they're actually real. And one of those things, and this all stems from the simultaneity arguments, that is, simultaneity is relative, is the twin paradox and why time is measured differently for different observers. Remember that one of the effects from relativity is something called time dilation. That is, a moving clock is observed to run slow. Okay, take a second to realize what that says. That's not an optical illusion. If a clock moves by you at a particular speed and you look into the spaceship that has the clock on it, then you will measure the time on that clock to be running slow. Now, somebody in that spaceship could do the same to you, and you would measure, the spaceship would measure time running slow compared to them, as long as they were in, both cases were in inertial frames. That was not accelerating. And then the question is who's right? And of course, the weird headache-inducing answer is they're both right. So anyway, what do we do with this? Well, let's take the space-time diagrams and see what we can do with this. And later we'll use an algebraic approach. I want to remind you of a couple things with the space-time diagrams. We know that there are special lines in the space-time diagrams, namely the 45-degree angle is a line that marks the path of light. And that would be true for anywhere. This is from, say, a light signal that's emanating from somebody at the origin. But if somebody were located here and sent off a light signal, it would, too, take a 45-degree path. Okay? And the thing that we want to remember is that if we look at lines, say paths, in a space-time diagram, we can look at the slope, that is, this time, right, or delta t, and this position, or change of position, delta x, and we know that the slope is equal to 1 over the speed, okay? Because if you think about it, the rise is delta t, and the run is delta x, so it's just 1 over v. And that means that for something moving at the speed of light, the slope is equal to 1, right? For units where we are using, say, light years or light seconds for x, and years or seconds for t. And I'll just point out, too, that we often use CT. We'll call that W is equal to CT, and that allows us to use these normal units. Okay, where does this all buy us? Well, one thing it buys us is that we can look at how things might be causally connected. And it's not necessarily whether they're above or below the light cone. It's just looking at the relative positions of two objects, namely, or events. Say name two events, A and B. If the slope is steeper, that means it takes a smaller speed than the speed of light to get from A to B, or from A to send a signal to cause B. We would call that causal, or at least potentially causally connected. If, on the other hand, A to B had a slope that were shallower than 1, these would be acausal. There's no way for A to communicate to B in time, in the time that separates them, without traveling faster than the speed of light. And that is at the basis of special relativity. Okay, so we've talked about that in the lectures, right? And so now we want to consider the case of two people that are moving and what they measure. And that's basically the heart of the twin paradox. So if we just scroll over, and fortunately, if you're a physics teacher and you happen to have a twin brother, this makes teaching the twin paradox easy. So I've got my twin brother Sean over here, and yours truly over here. And say we decide we're going to try this experiment. Sean is going to stay at home, and I'm going to get in a really cool rocket ship and fly at 80% the speed of light to a planet that's 10 years away. So I'm going to go out 10 light years and back 10 light years at 80% the speed of light. The question then is, what would these two twins observe for their time? In fact, if we had clocks running on the spaceship and at Earth, would they agree? Would they be the same ages? Well, as it turns out, for somebody traveling at 80% the speed of light, the rocket would only take about 25 years as measured from the Earth. As measured in the spaceship, right, as the time on the spaceship is only 15 years. In other words, when Megan would arrive back on Earth, she would be only 15 years older, so maybe a little bit more gray in her hair. Still cute as a button, though. And John would look like our dad. So the question is, we've talked, sort of the paradox comes in with the relativity of time. We have talked about and we have read about how both observers can say the same thing about the other. That is, I'm in a rocket ship, I go off to a planet, come back. I could argue that I'm standing still and the Earth is moving away from me with Sean on it and then coming back. Sean, of course, is on the Earth and he sees me blast off a rocket and come back. And so to him, I'm moving, right? And if that's true, if the two cases are relative, right, that I can say one is moving and the other person can say the other is moving, then why should it be that one twin is a different age than the other? They should have both aged at the same time. Why do their clocks not agree? And this was a huge conundrum, and you can explain it very neatly. There are lots of different ways that you can explain the twin paradox, some of them much more complicated than others. We're going to use the space-time diagrams, and then ultimately we'll use algebra to do that. So now, what I'd like you to do, I'm going to pause this and we'll come back to that, is I want to make sure that in your notes you have either some graph paper or that you can set aside some graph paper so that you can draw this diagram. That is a time axis that goes out to about 25 and a space axis that goes out to about 15. Okay, and you may want to draw in the light cone if you like. And the setup is that we're going to be going out to 10 light years, right? And we know that the total trip as seen from the Earth is going to take 25 years. So we know that the turnaround point is after 12 years as measured on the Earth. So we know we're going to be drawing this kind of diagram, okay? So I'm going to pause here and make sure that you get yourself some space and maybe set up a couple of diagrams so we can look at this, and then I'll come back and you can run the second part of this video. Awesome.